Last time we started chapter one. Chapter one is fairly straightforward. We talked about some concepts like rounding. We talked about estimation, why it's important in general. We're going to finish off chapter one by talking about general problem solving. How can you solve a problem, especially a word problem, because word problems are kind of difficult. Well, what we're going to do is we're going to use something called Polya's 4 steps in problem solving. Polya was, I believe, a psychologist or a psychiatrist who studied, how the mind works and how we are able to learn and how we are able to solve certain types of problems. The first step in the Polya method, you need to understand exactly what you're being asked. If you read a problem and you don't know what the heck it's asking you, you're going to not be able to really do anything. So you need to understand what is being asked. Honestly, start by reading the problem several times. Your first reading can just be kind of an overview. You get a basic understanding of what's going on. In the second time you read through the problem, start writing down some key information, some of the numbers you see in the problem, what they're supposed to represent. Also, in your second reading, write down, and I mean physically write down on paper, what in the world you're trying to find. What is the problem asking for? So you want to have a full and thorough understanding of what you're being asked, why you're being asked it, and so on and so forth. Now, step 2 is going to be about devising a plan. Devising a plan. What that involves is starting to think about different strategies that exist out there. And there are plenty of strategies that exist in math for different types of problem. No two problems that are at least different from each other probably require the exact same strategy. So you're going to have exposure to a lot of different strategies out there. So you can use inductive reasoning to look for a pattern. Inductive reasoning involves you making a conclusion that is likely to be true. So if you see a pattern forming, you can hope that the pattern is going to continue, and you can use that to manipulate the odds in your favor. You can make some kind of list or table. Estimation is important. Rounding or getting a ballpark of what the final answer should be. How many of you pay rent? You pay rent, or you pay a mortgage, you pay something like that. Okay, my rent is about $800 a month. Or if I'm renting like a house and I'm paying for all of it, it might be $1,200 to $1,800 a month, something like that. So in chapter 8, when we do mortgage calculations, when we calculate the monthly payment required when you buy a house, if you get a monthly payment that's 23 cents, you're probably wrong. If you get a monthly payment that is $3,756,000, you are probably one of those Uber billionaires. You're probably, Jeff Bezos, who is the CEO of Amazon. But if it's a reasonably priced house, somewhere in like the 200,000s, which is a normal priced house, you're not going to have a payment that high. Your payment is going to be somewhere in the ballpark of $1,000 to $2,000 or $2,500 per month. So you can estimate, just looking at the problem, you can get a ballpark range of what the final answer should look like. So to throw out something that's ridiculous. You've made a calculator mistake or something like that. And that happens all the time. Trial and error is also a really nice method. There are some problems where you can just grind out every possibility till you get the right one. You can make sketches, you can make pictures. There's all kinds of different strategies you can use. There's even going to be some trick questions, questions that just try to trip you up. They'll have a really complicated question that it starts off with, and there's a lot of details they give you. And then the actual thing it's looking for is something real simple. So be careful on that. There might be sometimes they're just trying to catch you off guard. So don't assume that just because a question looks hard, that automatically makes it difficult. Step 3 is, kind of both the easiest and most difficult step if you think about it. Carry out the plan and solve the problem. Okay, that's great. So assuming you've done steps 1 and 2 effectively, step 3 is straightforward. Now, step 4 is really important. In fact, there's going to be some problems we solve where we need to look at what our answer is, and we need to go back and make sure it makes sense. We need to make sure it fits in with the problem. You might even do a mild calculation here or there. But step 4 is really, really crucial. We need to go back and look at it. So I'll give you a second to write that down. So these are called the Polyaz 4 steps in problem solving. So what we're going to do for the rest of this section, we are just going to look at some different types of problems. We're going to break them down using Polyaz 4-step method. The thing is, on the homework for this section, which by the way isn't due until next week, on the homework for this section, you're going to have a bunch of different kinds of problems. Some of them are word problems. Some of them are going to be hilariously easy. Some of them are going to be more difficult than they appear at first glance. But the idea is you need to sit down with the Polyaz method. I would literally write out step 1, step 2, step 3, step 4, and I would take it slowly and do it piece by piece. A man purchased 5 shirts, each at the same discount price. How much did he pay for them? What? How many of you read that and you're like, what? How in the world can you answer that question? Did this problem give you any information whatsoever on how much he would have paid for them? It just said he bought 5 shirts, he got a discount for them. Did it give us any hard and fast numbers? Were we talking digits here? No, we weren't. So you should immediately tell yourself something's wrong with this one. Let's see if the Polyaz 4-step method can identify an issue with it. Understanding the problem, we're given that 5 shirts were purchased. We need to figure out how much the man paid for them. Well, as we start to devise a plan to solve this, this is really going to just break down. Whatever the man paid for the 5 shirts, we multiply by, whatever the man paid for any one of the shirts, we multiply by 5. That's how much was paid for all of them. We don't know the discount price, though. There's a huge missing piece of information here. So we just can't solve the problem. And literally, Polyaz can help you identify that. Now, if you could probably read that one and immediately figure out that you can't answer the question. So this homework section for this section is going to have some trick questions like that, a few tricks where there's nothing to solve. Let's see if this one is a little bit better. By paying $100 cash up front and then paying off the balance at $20 a week, how long will it take to pay for a bicycle that costs $680? Well, this is going to assume there's no interest, because normally, especially if they give you the bike and then you just make payments on it, normally there's an interest rate. And we'll talk about interest in more detail later. But assuming there's no interest and we're just paying off $20 of the balance each week, the cost of the bike is $680. We're paying $100 right up front. So we should know $680 minus $100, there's $580 left to pay off. And we're going to be paying that off at $20 per week. So the plan is pretty simple. You subtract the amount you paid off right away. You divide the rest, the amount you didn't pay off, by $20, and that'll tell you how many weeks it's going to take to pay that off. So enact the plan. You still owe $580. Divide that by $20. It's going to take you 29 weeks, a little more than half a year, to pay off the bicycle. Now, what you want to do, step 4 is pretty critical. You can Perhaps you could say I deduced exactly how much I have to pay each week. So I don't need to check my answer because there's only one way it could have gone. Perhaps for this problem, you're right, but there are going to be other problems where it will really help you to double check your final answer. Another thing it does is if you double check your final answer, you can figure out if you made a simple calculation mistake or an arithmetic mistake at some point. So tell yourself, well, I'm paying $20 a week for 29 weeks. That's what I determined. That's $580 total dollars. Plus I'm paying the $100 up front. That brings me to $680, which indeed was the cost of the bicycle. So we're good. We're golden. And there's all kinds of different problems that you can look at. Let's look at something else that's interesting. Let's make our own problem. 6 friends, and their names are Joey, Monica, Phoebe, I think that's it. No, I think it's Chandler. Make sure I'm on the whiteboard, okay? Chandler, Ross, and Rachel are given 2 free tickets to the opera. And those are just 6 random names I picked out of nowhere. They don't mean anything. They're given 2 free tickets to the opera. How many different ways can those 2 tickets be given out to the 6 friends? Or in other words, how many different pairings are there between those 6 friends? So using the Polya method, there's a couple things we need to do. We need to find all the pairs of 2 we can make from a group of 6. In fact, that's going to be a really important concept whenever we get to chapter 11 in this course. In chapter 12, it's very heavily involved with probability. But we're not going to do it using any of those methods. We need to find all the pairs of 2 we can make from a group of 6. How can we do that? What do you guys think is kind of the easiest way? Well, maybe if I had 175 people and I had to find all the pairs of 2, that might be way too difficult for me to write out every possible pair. But if there's only 6 people and I only have 2 pairs that I have to make at a time, maybe it's going to be easy for us to just list out all the possible pairs. Does that sound reasonable? What do you guys think? Make a list? Because otherwise, how else would you do it? You'd have to invoke some higher level math that we just don't quite have yet. So here's what I'm going to do. I'm going to use J for Joey. I'm going to use M for Monica, P for Phoebe, C for Chandler, O for Ross, A for Rachel. And then I'm just going to start with Joey, pair him up with everybody. He can't pair with himself. So I'm going to say, all right, it could be Joey and Monica that go. It could be Joey and Phoebe that go. It could be Joey and Chandler that go, Joey and Ross that can go, or Joey and Rachel. So here's some of the possible pairings right there. Joey can't go with himself. Now I'm going to go to Monica. Do I have to worry about going Monica and Joey? No, I've already taken care of that right here with JM. So basically, Joey's already been paired up every possible way. We can cross them off the list. And now I can do Monica and Phoebe, Monica and Chandler, Monica and Ross, Monica and Rachel. And now Monica's already been paired up with everybody. She was already paired up with Joey. It doesn't matter which order we put them. They're just going to the opera together. It doesn't matter if Joey is the first ticket, Monica is the second ticket, or vice versa. That's irrelevant. Next up, we take Phoebe with Chandler. Phoebe and Ross can go. Phoebe and Rachel can go. Phoebe's been paired up with everybody. Chandler and Ross. Chandler and Rachel. Now Chandler has been paired up with everybody. And then finally, Ross and Rachel can go together. Ross has been paired up, but then Rachel's also been paired up with everybody else. So it appears to me that in this kind of problem, it just makes sense for us to list out all the possible pairs. And then what are we going to do? To answer the question, we need to just count. It wants to know how many different ways can these 2 tickets be given out. We just need to count all the possible pairs of 2, and we're done. And it looks like it's going to be 5 times 3, 15. So there's 15 pairs of 2 that can be formed from these 6 friends. And that's it. Again, if we had 175 friends and we wanted to find all the pairs of that, no, we don't want to do that. We can't list them out. We're going to be here for a while. I promise you, you'll be here for a long time. But the numbers aren't too large that it doesn't make, or that makes sense that we can use a list. Step 4 of POLIAS, where you verify what you have. It's not like we can work backwards for a calculation. We know what we did was right just from looking at it. You can double check your work. You can tell yourself 15 sounds like a reasonable number. It's not like we got 75 trillion as the answer. It's not like we got 0 or 1 or 2 as the answer. Those don't quite seem large enough. So the 15 seems like a reasonable answer for this. So continuing on, you're an engineer programming the automatic gate for a 50-cent toll. So you go to the toll, and most people might pay with credit card, or they might use the toll tag system, where they just put a little thing in their car that automatically scans them and it just charges them later or from an account. But you're going to have some people who want to pay with change. So you have a 50-cent toll. The gate accepts exact change only. So if you give it, you have to give it exactly 50 cents, no more, no less. It also doesn't accept pennies. So it's going to accept half dollars, quarters, dimes, or nickels. How many of you knew we had a $50 coin? 50-cent coin? Yeah, I mean, I guess you know about it in theory, but how many of you ever had one? Maybe. Yeah, maybe, I'm sure I've had one at some point, but the $50 is just not very popular. There's also a 75-cent coin there used to be, but that one was very unpopular because that one didn't add up very well. 4 of them is $3. It's just not something that a lot of people would want. So in other words, we need to find all the combinations we can have that add up to 50 cents using nickels, dimes, quarters, or 50-cent coins. So let's see, we need to devise a plan for this one. Again, it seems like just making a list, checking it twice is going to be the best thing that we can do here. We just kind of say, okay, just start thinking about them and see if you can get every possible combination. So it's just a little bit of logic. So you can use a nice little list here. You have half dollars, quarters, dimes, and nickels listed along the top. This is a good method. Each row on this table is going to be one of the possible combinations. So you can do $1/2, 0 quarters, 0 dimes, 0 nickels. That's exactly 50 cents. You toss that in the little change machine or whatever at the toll booth, and you're good to go. The little gate will open, and you can go. Next up, you can do 0 $50, 2 quarters, no dimes or nickels. That'll work. And so as you can see, we move down the list. Each row represents a different combination that the machine should accept. Do Can you think of any combination of those 4 coins that can add up to 50 cents that's not listed here? Ooh, let's see, 10 nickels you can do, 5 dimes you could do, but that's right here. 2 quarters is obvious. You could do a quarter, 2 dimes, and a nickel. You could do a quarter and 5 nickels, 4 dimes, 40 cents, plus 2 nickels, gives you 50 total cents. It looks like this list here is pretty exhaustive, and that's exactly a way that you could organize this list. So you'll notice we didn't use any magical mathematical formula. We just sat down, we thought about the problem very clearly, and we said, hey, you know what? This list takes care of everything. And so now we can count. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different rows here. So there's 11 different combinations of change you can use to make 50 cents. Again, no pennies. Pennies should just be outlawed. You look back, you check over your answer, you just very thorough, try to think of anything that you could, might work, but it should all be listed there. So we kind of already did a problem just like this. Yeah, we already did a very similar problem as that last one. So let's look at this last problem we did. We talked about 6 friends who were getting 2 opera tickets. 6 friends who are getting 2 opera tickets. It doesn't matter what order they go. Joey and Monica is the same as Monica and Joey. Let's mess with that a little bit. Let's change that up a little bit. What if these 6 friends are running in a race? How many different ways or how many different top 2 finishers can there be? So instead of just, oh, well, it doesn't matter who we're calling the first ticket and the second ticket to the opera, now we're running a race, and now there's first place and there's second place. So earlier we found all the pairs of 2 we can make out of a group of 6. We're doing the same thing, except we're adding one extra thing to it. Once you have a pair of 2, they can cross the finish line in 2 different ways. One can finish before the other. So this initial list we worked up is still a really good list, but we need to add on to it. The top 2 finishers can be Joey and Monica, but it could be Joey first, Monica second, or it could be Monica first, Joey second. The top 2 finishers could be Joey and Phoebe, but it could be Joey first, Phoebe second, or it can be Phoebe first, Joey second. So now what we say, now the order of the 2 finishers matters. Earlier it didn't, now it does. It just depends on the context of what you're working on. And what you can see is that it clearly just doubles what we had earlier. So there's going to be 30 total ways that this can go, and we're just adding on to it. So now we can see there are 30 total ways that we can have top 2 finishers in this race. If you want to know all the number of ways you can have your top 3 finishers, that becomes even nastier. That becomes an even much bigger problem than that. Because you can think, all right, how many different ways can I make a group of 3 of these friends from a pool of 6 of them? And then I also have to calculate how many ways I can rearrange those 3 friends on top of that. So it becomes an even more complicated problem. So you can see very quickly that if there was like 12 friends and 3, and we're talking about the top 3 finishers of a race, you would not want to use a list. You would be there for a while. You would probably make a mistake because it's hard to get a good system for knowing when you've already included a group of 3 or not. So what we're going to study in chapter 11, we're going to learn about things called factorials, combinations, permutations. Those are going to be tools that we use to count up things like this. Now, why in the world would we care about counting up things like this? How many of you have ever played poker before? How many of you would like to play poker? How many of you think gambling and games like that can be a lot of fun? Absolutely. How many of you know how much they win at the World Series of Poker? They'll win 10, 15, 20 million dollars. And I mean, that's some legit money. If you won that, you would never have to work a day in your life again, unless you want to eat caviar every day. You can just have a nice, comfortable life. So things like that, things like blackjack, things like going to the casino, all of those things are inherently things that are related to probability. And if you understand probability, you can understand whether or not you have an edge in a game or what move you should make. In poker, you have a deck of 52 cards, and you're going to get a hand of 5 cards, right? If you're playing kind of standard old school poker. Well, we can use combinations, which we'll learn about later, to calculate the number of different 5-card hands that are possible in poker. And then if you can calculate how many royal flushes are possible, which there's only 4, you can determine the probability of getting a royal flush or a straight flush or just a simple pair in poker. And then you can know what moves should you make. If you're playing Texas Hold'em, should you stay in or should you fold now and cut your losses? So there's all kinds of games, and probability and counting procedures like this are interesting. So you have a deck of 52 cards. You want to know all the ways you can get any 5 cards from that, so you can know all the 5-card hands possible. How many would you guess there are? Would you guess that there's 10,000 different 5-card hands? 20,000? 30,000? What if I told you you were way off? There are almost 2.6 million different 5-card hands you can get in poker, which is wild. That's a lot. So if there's only 4 hands that are royal flushes, the best hand in the game, out of almost 2.6 million, do you think a royal flush is likely to occur? Do you think you have a good chance of getting a royal flush? Absolutely not. So you don't bet on getting a royal flush. It's not going to happen, but in extremely rare cases. So let me get our next stuff figured out. So we have wrapped up chapter 1. Chapter 1 was just kind of a general, maybe review of a few concepts like rounding, estimation. We also learned some basic tools that can help you with problem solving. There's no one problem that you're going to solve exactly the same way as another problem, most likely. What we're going to study in chapter 2 is going to be something that does not at all look like math. It won't look like math in the traditional sense. Most of us think of math as numbers and multiplying things and all kinds of equations and graphs and functions flying around. That's not what chapter 2 is going to look like. That's not what chapter 3 is going to look like. Chapters 2 and 3 are very abstract, meaning we're going to use a lot of symbols that are meant to represent something. We're going to talk about a lot of things that are purely on a concept level, and it can be difficult to necessarily imagine what these concepts look like in reality, in the real world, if you will. So we're going to start chapter 2. We're going to learn something called set theory. Set theory. And we'll start with the mathematical definition of a set. A set is a collection of objects whose contents can be clearly determined. So think about, you have a box of Christmas ornaments in your garage or in your closet somewhere. You could say the set of all Christmas ornaments are the objects in the box. You might have some tinsel, you might have some, Christmas tree ornaments. You might have some lights that you hang up. Now, I go all out all year for Christmas. I also go out for Halloween. I decorate the outside of my house. I decorate the inside of my house. I love it. I love it so much. Like October 1st hits, that's like the happiest time of the year for me. October 1st through December 25th, best time of the year, easily. Fall is my favorite season. So on November 1st, then I take down my Halloween decorations and I put up some fall decorations. I literally go down the street and I purchase some bales of hay and I put bales of hay in my yard and they leave a nasty yellow stain on my grass, but I don't care. I have like yellow lights and I have these little scarecrow things and I have a fall wreath that I put on my door. And then Christmas time comes and, I'm just like skipping around the yard. I'm like a happy kid. That has nothing to do with math, but I wanted you to know that, okay? I felt that you needed to know how much I love Halloween and Christmas. You know what the worst day of the year is? December 26th. I hate December 26th. It just happened. When December 26th happens, I get like sad. I get a little bit depressed. The holiday's over. The best time of the year is over. You know what the second worst day of the year is? January 1st. Because it's a new year. It reminds you that you're getting older and that you can't get back that time. And the holidays are done. The best time of the year is done. You know what? Holidays are not fun. Most of the holidays at the first half of the year. Valentine's Day, my girlfriend and I, we give each other stuff, but it's not like I'm going to decorate my yard with Valentine's Day stuff. It's not as fun, is it? So Valentine's Day is not as fun. So yeah, a lot of the best holidays, October 1st through December 25th. If I could be in the Matrix and just relive that, like, all right when December 26th hits, I just reset to October 1st, I would be the happiest person alive. But that's not possible. So life goes on. Anyways, so a set is a collection of objects whose contents can be clearly determined. What we call the contents of a set are its elements. We don't really use the word members. Elements, the elements of the set, the things that are in it. A set must be well defined, just meaning you know what's in it. Now, that doesn't mean you necessarily list all the objects in a set. If I talk about the set of people who live in America, who live in the United States, there's almost roughly 400 million people that live in the United States. So is it practical for me to just write out the name of every single person who lives in the US? No. First of all, even the US Census may not be able to determine everybody. There's a lot of problems that always happen with the census. But second of all, 400 million names is a lot of names. It would fill up this whiteboard, like thousands, even millions of times over. So just because I can't write out every member of a set doesn't mean I can't visualize it in my head or have an understanding of what it is in my head. So a set does not always have to be listed out explicitly. Now, when you're talking about a set, if you do choose what is called the roster method, where you do just list out the elements, you're going to use these special set braces. You must use them. If I just list out Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, if I just list those out and I don't put set brackets around them, they're not a set. So those brackets are entirely necessary. They are mathematically precise and required. So anyways, we can use a capital letter to represent a set. Maybe we can use a capital W, W for the word week. And we can use capital W to represent the set of days of the week. And there you go. W equals. Notice that there's an open set bracket to start. And then we just list out the days separated by commas, Monday through Sunday. So this is a great example of a set. You can, let's say you have the set P, capital P, and you say capital P equals, capital P is the set, Washington, John Adams, Thomas Jefferson, James Madison, James Monroe. It's James, right? James Monroe. I think it's James Monroe. A word description of that set, well, that's just the set of the first 5 presidents of the United States, or at least their names. So that's cool. The next president would be another Adams. It was John Quincy, who is John Adams' son. So when George W. Bush was president, that was only the second time in U.S. history that someone was a president just like their father had been a president previously. So that's kind of interesting. There are different ways you can write a set. So you can use a simple word description. You can just say, this is the set of all Americans, of all U.S. Americans, whatever. You can say, this is a set of all different car models that exist out there. RAV4 or a Chevrolet Cavalier, the car of the gentleman. No, that's not true. I drove a Cavalier in high school, and it was old. It got me from point A to point B, but it got totaled. I won't say how or why, but it was totaled. I miss it. So you can just describe the set itself, or you can use the roster method. You think about a roster on a basketball team or a soccer team or a baseball team or a football team. All you're doing with a roster is you're just listing out the members of the team, right? So yeah, the roster method is very straightforward. Let's say set C, I'm bringing set C back, is the set of US coins with a value less than $1. We kind of talked about this earlier. So if I wanted to list that out in roster notation, it would be C equals open bracket, penny, nickel, dime, quarter, $50. Those are the ones that are still popularly in circulation. Like I said, there used to be a 75-cent piece, but that never really caught on. So you can use a word description, you can use roster notation, or you can use something called set builder notation. And this is going to be important, especially whenever we need kind of mathematically precise ways to define a set. If you were talking about the set featuring the days of the week, you could say something like this. Set W is all X, all elements X. This vertical bar means such that. It's just your way of transitioning into what X is going to be. All elements X such that X is a day of the week. So notice I don't have to list out Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday with the roster method. Why do we want to do it this way? We're going to see some examples very shortly of different sets where we're going to use some mathematical relationships. We're going to say all numbers greater than 5 or something like that. So it doesn't make sense for me to list out all numbers greater than 5. Can you even do that? How many of you believe that you can write down every number which is greater than 5? You can't, can you? How many numbers are there greater than 5? A lot. There's infinite. Yeah, there's infinitely many numbers greater than 5. So we're going to run into things called finite sets that have a finite number of elements in them. We're also going to have infinite sets that have an infinite number of elements in them. So we're going to need set builder notation just depending on what you're trying to do to help us with that. So if you have the set A is all X, such that X is a month that begins with the letter M. No imaginary months. You're not allowed to make up months. Well, okay, that's a very, very wordy, long way of saying, oh, well, March and May. March and May are the only 2 months that start with the letter M. In other words, all we've done was we've converted from this set builder notation into roster notation, where we just list out the elements ourselves. So again, so far the set theory that we're learning doesn't seem horribly complicated, but I promise you it's deceptively simple, because it can get a little bit complicated quickly It's also, like I said, very abstract, meaning when I'm thinking about these things, I'm thinking about vague concepts, not necessarily vague, but I'm thinking about concepts that you may not, like, I'm not literally showing you the set of days of the week. Like I have them in my arms or something. You have to think about it in an abstract way on paper. Whereas when we're talking about money, it's a lot easier to imagine $2,000 sitting in your hand, your monthly payment on your house or something, or even $2,007.53. You can imagine that much money in your hand. It's a little less abstract. So that's all I mean by abstract. It doesn't have to mean difficult. It just means that it's a little bit less tangible. It's more in theory or concept. So now we're going to start getting some more abstract with it. We're going to talk about something called the empty set. And once we define it, you're going to say, why in the world would we even care about this thing? The empty set, also called the null set, which you'll never hear me call it the null set, don't worry. The empty set is this set that contains no elements. It's exactly what you'd think. It is a set that has nothing in it. Raise your hand if you would say, why in the world do I care about the empty set then? It's got nothing in it. Raise your hand if that's what you're thinking, honestly. I completely agree. But let me spin it a different way. Think about numbers. Don't we need a number 0? Even though 0 represents the absence of something, even though 0 means there's nothing there, you still need to have a number 0 in theory, right? It still means something. If you have $0 in your bank account, even though there's nothing there, that's still meaningful to you. That means, well, I don't have any money. I can't go purchase, that Slim Jim. So interesting that my mind went to Slim Jims. But anyways, 0 still means something in numbers. Well, the analog then in set theory is we need an empty set. We need a set that represents nothing, that represents emptiness, meaninglessness, because sometimes it's just going to pop up and it does have a meaning even though it's empty. For instance, if you have the set containing the days of the week and the set containing the months of the year, what do those two sets have in common? Is Monday a month of the year? Is August a day of the week? No, those two sets have nothing in common, do they? So all I would do is instead of saying there's nothing in common, I would just say, oh, their intersection is empty. That's going to be the word we use for it. So I can quickly define what it means for them to have nothing in common. I say there's 0 things between them. The empty set, though, is a set. The empty set is not the number 0. It is a set that is empty. Think about your Christmas decoration box. Well, once you've put up all your decorations and if you used everything, your box is empty. The box is the set. The elements in them, there's nothing in there. It's empty. It's gone. So that's a good way to think about it. We can use this symbol. This is the common symbol. It's like the Ghostbusters symbol, where it's just a big old circle with it crossed out. That means the set that has nothing in it. That's going to be the symbol we use. You could also be really sarcastic, and you can open a set bracket and then write nothing and just leave nice blank space there and then close a set bracket. But again, that's kind of sarcastic, like, this is a set but has nothing in it. Yeah, you can write that, but this is the more common symbol, to use the circle with the line through it. Here's an example of an empty set. All numbers that are both less than 4, but also greater than 10. Can any of you think of a number that is less than 4, but also greater than 10? No made up numbers allowed. No, you can't. It's impossible, right? So it sounds cool, set of all numbers less than 4, greater than 10. If you don't think about it, it sounds like a really cool, neat set, but it has nothing in it. So that is the empty set. It's equivalent to the empty set. Or all X such that X is a fawn, a female deer or something. Is a fawn a deer? Okay, a baby deer. A fawn that speaks. Now, unless we're living in the Bambi extended universe, there's no such fawn that can speak. So that's going to be the empty set. Okay, I'm going to take attendance. Please stay in.